take the stage and present another short case history regarding settlement analysis, some field quality control, and monitoring issues. So without further ado, I just want to make sure that everybody is able to track my screen. Switch to presentation mode, and in order to avoid you keeping longer in this busy time of the day, let us start now. So the title is labeled as Settlement Analysis and Foundation Engineering Solutions to discuss both the roles of numerical analysis and monitoring at the same time. A little bit of introduction from Geodestek site. We are based in Ankara, Turkey. The company has over 22 years of experience. We are a university spin-off company, and we are highly integrated with research and development activities in our environment. Besides construction works and contracting within the scope of geotechnical engineering, we basically try to cover as much as we can in terms of meeting the demands of the geotechnical community at international and national level. For a long time, we have been carrying out geotechnical investigation activities using our own drilling rigs, CPT rigs, and other types of critical equipment. We are highly active in geotechnical design, advanced geotechnical design. We are providing services and products in terms of software acquisition and training, custom training or public trainings with rock science software tools in your region. We are performing field quality control services, operating a soil and rock mechanics laboratory, and just dealing with research and development, mainly focusing on developing our in-house manufactured geotechnical monitoring equipment at Middle East Technical University. So the monitoring aspect of the story is labeled as GeoEns, and pretty much within Turkey, we can probably pronounce that we are the single presenter of these products and services as a turnkey solution. So if you want to just reach us out and say hello, would be happy to meet in person. You may record our contact information. If you just want to browse our products, which are directly designed, conceptually designed, manufactured, and installed by our team in terms of geotechnical and structural health monitoring, please drop us a line so we can talk. In terms of the design, we have been heavily involved in most of the critical projects in Turkey, including different sectors such as mining, industrial facilities, transportation infrastructure, residential complexes, and other applications. At majority of the projects that we were involved in, we were just met with high demands, project demands, and let me say this in another word, sensitive structures, settlement sensitive structures, lots of precautions to be taken, and projects which any failure may have significant consequences. So it's all top work as we're trying to handle as much as we can. So that's it from me for now. I'll be joining you later on, but please let me hand the stage over to Dr. Tolga Bilge for the representation of our case study 1.
Thank you, Anıl, and hello and good afternoon to everyone. Let me share my screen basically we are going to use the same presentation, but since we are in different offices, and right now I'm hoping that you can hear me well and you can see my screen. I guess it is okay for now. So it is always nice to meet geotechnical engineers from different parts of worlds. We know that there are quite important and technically interesting projects that are going on in this region, and we are definitely really glad to be with you today. In the remaining parts of this presentation, as Dr. Yunatcı mentioned, we are going to focus on two recently completed projects, which include both numerical assessments and field monitoring. So let's proceed to talk about what were the geotechnical problems and what we did in these projects. For the first one, I'm going to talk about an industrial facility. Well, you know, when the project is a bit critical, there are some legal obligations, so I'm not going to directly provide the name of this project, but it will not stop us talking about the geotechnical problems and the mitigation measures. So we will talk about geotechnics, don't worry about it. The project area is located in the Black Sea region of Turkey, and it is quite close to the coastline, as you can see from these figures. It was planned to complete the project in 4 phases. We got involved into it during the first phase. At that time, site investigations were going on at some regions, but they were also performing monitoring and even constructing piles at some other parts of the area that was allocated for the first phase. Well, all this happened more than a year ago. Right now, almost all of the geotechnical works of the first phase have been completed, but superstructure construction is still going on. And if you wonder about the other remaining phases, the client is still working on optimization and feasibility issues, but hopefully they will start in the near future. So as part of the first phase, it was planned to construct around 60 structural units, and we, as Geodestek, were responsible for 23 of them. All those units, well, they have different features, the soil profiles under them, there exist variations, structural properties, and the expected performance, they all vary from one unit to another. So we had to deal with different problems. Some of them were governed by static loading conditions, yet some of them were related to seismic performance. For today's GeoTalk, I selected a structure under which we designed a ground improvement system, including use of preloading and drain columns. Right now, you can see the location of this unit. It is relatively closer to the coast, but there still exists a distance in the order of 1 kilometer. There exists a river flowing in close proximity to the project area, so we have water around it, as I'm going to mention in the following slides. But for today's talk, we are going to talk about some storage tanks. Their locations on the general layout indicated by this red rectangle. A closer view, you can see it from there. In order to evaluate the subsurface profile, a site investigation study was performed. Within the scope of these investigations, 9 boreholes were drilled. You can see the respective locations of those boreholes, those relatively smaller yellow and blue circles. Well, they sampled soil and rock. They performed some laboratory tasks. And even there exists one geophysical exploration as well. So we have some data. And let me show you some factual data, the findings of the site investigation study, so we can feel the nature of the problem. Here you can see the lithological cross-section prepared based on those borehole logs. We have a randomly deposited fill layer, which I'm going to cover next. Following it, there is a very thick alluvium layer. And basically, these two are the sources of most of our geotechnical problems. And they are underlain by some dense to very dense sand and gravel units, which are cohesionless in nature. And then we have an alternation of claystone, siltstone, and sandstone, which is basically a weathered rock unit. As I mentioned while introducing you the project, it's a huge area. So more or less, we encounter these units everywhere, but especially the made ground alluvium with its varying properties and the weathered rock alternations, they were everywhere. Thickness of the fill and alluvium vary from region to region, and based on this variation, the extent of the geotechnical problems vary as well. For this case, the thickness of this alluvium layer is in the order of 45 to 50 meters, and it was the main concern for us. So let me talk more about those units and provide you some available information. But let's start from the fill unit and let me tell you the story or the history of this material. Right now you can see the general description which was provided from boreholes, and there exists a photo so you can see how it looks in the field. It is a heterogeneous material, and we learned that it was randomly deposited over time. Based on the information provided by our client at the beginning, it was deposited in 2 stages. The first one took place almost 5.5 years ago, and it was to an elevation level of plus 6.0 meters. It was done to grade the project area and as a mitigation against flood risk. It's what we see per provided information. And then around January 2021, the second phase took place, and the overall elevation of the project area was increased by 1 more meter to reach plus 7 meters. All these operations took place before we got involved in the project. By the way, we joined to the design team around August 2021 and started working for this specific unit around November 2021. So the field had been there for more than 10 months when we started working for this region. When you look at the whole project area, the thickness of this material, it reaches to 8 or 9 meters at certain regions, but in this part it was in the order of 4 to 5.5 meters. Considering that it was not an engineering field, during site investigations it was mainly aimed to determine the thickness of the material rather than performing tests on it. Yet for the natural soil or rock units, we have some valuable investigation data, and it involves both in situ and laboratory tests. Let me provide you some more information. But I have to say that we were not a part of the team when they planned or executed those studies. When we started, they just gave us the factual report, and then we started working on it. As part of the field studies, 9 boreholes were drilled, as I mentioned earlier. Depths of them vary in the range of 50 to 80 meters, so they got an idea about what was happening in the first 80 meters from ground surface. Standard penetration tests were conducted at all of the boreholes, and yes, we are still using SPTs quite often. I wish we had a chance to have some CPT data. By the way, at different parts of the area, we as Geodestek performed some CPTs, but it was too late when we started working for this one. And when we look at the boreholes, well, 2 of them were reserved for pressure meter tests, 2 other for field permeability tests, and they provide quite useful and valuable data for us regarding the design. These tests were mainly performed on the silt and clay mixtures, in other words, our alluvium layer. Here you can see the variation of these test data. There exists a slightly increasing trend with depth, but in general, SPT block counts are in the range of 5 to 20, indicating the rigidity or consistency of this alluvium. Well, it is varying from soft to medium stiff. And this unit is totally saturated considering the depth of groundwater table as mentioned herein. On the other hand, permeability tests, they are again quite useful, and they indicate that this material has relatively low permeability. But for fine-grained soils, it is not a surprising information, but it is definitely important to have quantitative data. And what else do we have? Let me move on to the next slide. Well, we have some laboratory test data. Classification tests were conducted, and it was pointed out that this alluvium can be described as silt or clay of high plasticity, but mostly NH type material and some CH type soils as well. As I mentioned before, we encountered this alluvium almost everywhere in the project area. At certain regions, it involves relatively low plasticity fines, and there exist some non-plastic silts or sand and silt mixtures as well. But in this region, they're mostly fines with high plasticity. The general variation of index test data with depth is also presented herein. There exists some scatter, but it is still possible to narrow these ranges. PI values in the range of 25 to 40, liquid limits in the range of 50 to 70. The amount of fines, well, it is possible to say that it is higher than 80%. And aside from them, we got some engineering test data as well. These cohesion and friction angle values, they were obtained from undrained, unconsolidated triaxial compression tests. Their direct use is open to discussion, but considering that we have some in-situ test data too, it is definitely good to have them to increase the data diversity. And at the end of the day, we also observe that they are not contradicting with each other. I mean, lab and field data. And what else do we have? We have consolidation test data, which was vital for us considering all these filling operations and also thickness of it. And this data definitely indicates that this material is quite compressible in nature, considering those relatively high CC or CR values. On the other hand, when we look at the other units, I mean our cohesionless soils, very dense sand and gravels, and also the weathered rock alternations, well, we don't have too many data, but we think that it's okay considering that they are encountered at relatively deeper levels. In other words, at least 50 meters from ground surface, and they are definitely stiffer and stronger compared to the other formations encountered at this part of the project area. So, based on the available data, we developed a 3D soil model. Considering the lithological cross-section that I presented before, it may be possible to create an idealized profile, a more simplified two-dimensional model. But we had a chance to use rock science settle 3 for the settlement analysis, and it allows us to model the spatial variation of these subsurface units. Considering the existence of relatively thick compressible units, we believe that settlement response will have critical importance, and we decided to use the abilities of the software product to its full extent. Here you can see the assigned engineering properties for the subsurface units, which were definitely selected based on the factual data. It is just a summary of a detailed data assessment study, but from my perspective, it is the most technically interesting and entertaining part of the project. And this simple table would constitute the basis of our geotechnical assessments. Now, before going further, let me say a few words about our structure, the last stop to cover before talking about our geotechnical concerns. As I mentioned, we have different structures in this project, but this one is a storage tank. It was planned to be constructed on a raft foundation having dimensions of 23 by 29 meters, depth of foundation 1.2 meters. The structural induced stresses varying in the range of 45 to 50, not a huge difference. This is the non-factor service load conditions. We are going to use it since settlement problems will be the most critical thing about this project. But in any case, obviously, it is not a very heavy structure. And based on the information provided by structural designer, we also observed that no tensile stresses or critical lateral loads, they were not expected under the foundation. And the settlement tolerances, they define it in two different ways: 4 centimeters of total settlements and an angular distortion of 1/500. These limits are relatively lower compared to a conventional structure to be constructed on a mat foundation. So after covering them, then we are ready to talk about, after having this lengthy introduction, then we are ready to talk about the geotechnical concerns, but I'm hoping that we all have an insight about the geotechnical features of the project area now. So the randomly deposited fill is a concern. And by the way, it is a concern for the whole project area. So when we started working for this unit, we already had some experience on how to treat this problem. I mentioned that it was randomly deposited, so it is on consolidation under its own weight was probably still going on at that time. And we never consider it as a proper foundation soil in our practice. So having a made ground was a concern for us. Aside from it, we have a very thick and compressible alluvium layer at the project area as well, just under this field. Considering the thickness of the field and also the fact that it was deposited relatively recently, it is possible to conclude that the consolidation settlement process is still going on under this field. By the way, we had field evidence regarding this problem when we started working on this unit of the project. Tight construction schedule, available machinery, I am sure all of us are suffering from them, and both of them were valid for this case as well. And relatively lower settlement limits, well, you know, it is not surprising considering that we are dealing with industrial structures. And actually, this 4 centimeters or the angular distortion limit that I provided, they were not the worst case scenario for us, not the lowest tolerances. In this project, we had to deal with some lower values for some other units. And last but not the least, the seismicity of the region. Well, Turkey is in a very seismically active region, so we have to consider this issue as well. So they are the potential problems for us, and let's see what we did about them. Before thinking about the possible problems under the structural stresses, first we had to evaluate the settlement response of the compressible units due to the existing field. As I mentioned earlier, we had some field evidence. There exists some settlement plates installed at different regions of the project area, and based on the collected data, it was possible to say that this process was still going on at that time. I mean, more than 1.5 years ago. So we had to work on it. We had to document it. We had to have an estimate about the degree of consolidation. For this assessment, we performed some numerical analysis by using the features of Settle Tree. It's a basic software product. I'm sure some of you have already used it. It allows us to define multiple layers, not horizontal in nature. It allows us defining different foundation geometries. It is basically using some empirical questions, but at the same time for consolidation analysis, the software has a hidden finite element motor as well. So what you're doing with this software, you can compare it with some other tools as well, and it's something nice to have it because it is relatively more practical to use this one. So we use the information provided by our client regarding the history of the field. As I mentioned, it was completed in 2 stages. We took this information into account, and here you can see the basic steps of the modeling. And then after concluding, after doing all those analysis, well, we determined that degree of consolidation was in the order of 50% at that time. and it was still expected to experience additional 30 centimeters of consolidation settlements in time, especially in a quite long time interval. Well, obviously, remember the tight construction schedule. It is not possible to wait that long because according to the original schedule, the construction of this unit should have been started in 10 weeks' time. I'm talking about that time period. And we know that if we construct some piles to reinforce compressible alluvium or bypass the made ground, then they will be subjected to negative skin friction effects. Socketing them into the incompressible, rigid and strong units, it is another alternative. Yet these formations were encountered at least 50 meters from ground surface. Although it was considered as a highly critical project, the client could not mobilize relatively stronger rigs to that part of the site at that time to construct relatively longer piles. By the way, when I'm talking about relatively longer piles, I'm talking about piles having length of 55 meters or more. And in this case, you may think that, well, they are not that long. We are constructing longer piles. Well, it is totally true, but at that time, it was a huge problem because there exists a number of construction activities being performed at the same time. And unfortunately, they didn't mobilize this equipment to that part. So we thought about it, and it was decided that we should accelerate the consolidation settlement process rather than constructing very long piles. For this purpose, it was jointly decided with the client to use preloading and the rain columns together. It is definitely an applicable solution, but in general, in ideal conditions, while designing these kind of systems, we prefer using small diameter and closely spaced elements in the form of wick rails. And we shared this view with our client, but unfortunately they informed us that it couldn't be possible to mobilize this equipment, and instead they could install sand rain columns having diameters of 80 centimeters. Which was a bit larger compared to what we had in our minds, but it was about the abilities of the machinery. And as I mentioned earlier, it was another concern. And when we got involved in the project area, the first phase of the project was still going on, and they had some experience with those relatively larger sized drain columns. And they say that we did it, we checked the performance of these columns and they are working properly. So based on this experience and based on this information, we say that, okay, it is noted and accepted, we are going to use them while designing the system. Well, it may not be the usual approach, and it didn't happen for all of the project area, but it was not the last item that was dictated by the client, because just after some time they said that, okay, we can give you an application pattern as well, and it will be 3.5 meters to 3.5 meters. It will be a square grid. Actually, it was not doing it on behalf of us, and we knew their intentions. They were just trying to provide whatever they could provide to us at that moment. So we decided, okay, we are going to use this one. And regarding the lengths of the columns, again, they informed us regarding their earlier experience in the field. They said that, okay, the longest columns that had been installed at this project site had been in the order of 45 meters. And by the way, we thought that even if they could install longer columns, probably they would not work efficiently. So we accepted this information as well as it was, and we went on accordingly. They shared the tools that they could provide for mitigation, And just after we said, okay, they started immediately installing the Saint drain columns. Such a rush. But once again, in our world, it was not something unusual. It is happening all the time. And the installation work was completed in a 3 weeks time period. As another tool, the client informed us that they had some additional fill material and they could use it as a preloading embankment at this area. So it was accepted to use it too. And they constructed an embankment having a height of 5 meters in 2.5 weeks time. So in this case, for this structure, we were asked to determine the amount of waiting period before the construction of this unit, of this storage tank. They tried to offer whatever they could and to see whether they could start construction in 5 or 6 weeks time. And by taking into account all of the given information, we created another numerical model. You can see some screenshots from our model. Again, we used Settle3 and its drain column and preloading application tools, and we check whether it is applicable, whether it is possible to complete these settlements in time or not. And here you can see the results of our numerical assessments. The time required for completion of the settlements due to the existing fields, I mean remaining amounts, and by the way, it was around 30 centimeters as I presented before. The required time was estimated in the order of a month. But as I mentioned, and as you all know very well, it was just an estimate. Considering the uncertainties associated with a typical geotechnical engineering problem, monitoring efforts, well, they were considered to be vital. And we recommended a plan including use of both settlement plates and piezometers so they can follow the settlement response, and also the dissipation of excess pore water pressure at the same time, so it will erase all the doubts about the process. Well, you know, asking for more is in our natures, but it is not possible to have what we want most of the time. And in this case, the client arranged a monitoring program that involved use of just the settlement plates. And as I mentioned before, they were quite good with those settlement plates, and you can see the locations of them. I will not go into the details of these discussions on how we try to convince them about the necessity and use of piezometers. I guess Dr. Yunatcı may say a few words about the importance of using those piezometers in his part later, but unfortunately we didn't have them. Yet the settlement plate data is still a very important, vital, and meaningful tool and data for us, because by using it, at least we can verify our settlement estimations with some instrumentation data. So the monitoring group started sharing the collected data with us periodically. So we used it for comparison, and we started comparing the predictions with the measurements. But in 2 or 3 weeks' time, I couldn't remember it correctly because it was a year ago, more than a year ago, we were informed that the construction schedule was revised and they will not start constructing anything for the next 6 weeks. Yet we had the data and we use it for verification purposes. Here you can see, by the way, our prediction and the data coming from the site. The lower curves, well, they belong to our area that we are going to construct the storage unit. And here you can see a comparison of the estimates, including both the results of SATL analysis and the hand calculations. They are not contradicting, but performing analysis, SATL analysis, it is relatively easier, at least according to me, but they are not varying in a huge range. And the lower gray figures, well, they belong to this area. And well, not a bad fit in our standards. And the additional waiting period due to the revision in the schedule, well, it provides us some buffer considering the lack of piezometers. So based on these results, we concluded that settlements due to existing fill would not be a problem anymore. And when they waited for around 2 months, they actually had a chance to complete the settlements under this additional preloading embankment as well. So we can move on to talk about what might happen under the structural loading, because you know the main idea is not to improve the soil, to accelerate the whole process, but to construct an industrial structure. But as you know, we focused on a different problem up to now. Let's focus on our structure. Considering the dimensions of the mat foundation and the structural stresses, just as a reminder, it is a rectangular structure. It will be constructed on a mat, 23 by 29 meters. It is the dimensions of the foundation. The structural induced stresses, they are varying in the range of 45 to 50 kPas. So we did not expect a general bearing capacity problem for this one. And the preloading and the drain column applications, well, we believe that they should be effective against the consolidation settlement related problems as well. And considering that this load was kept there for a prolonged duration, we didn't expect any more consolidation settlements by taking into account the order of structural induced stresses and the dimensions of this foundations, as I mentioned. So nothing serious should happen, but in our local practice, local engineering applications in Turkey, we do not construct anything important on fill. It is not a good engineering practice. And well, you may say that this main ground should possibly be compacted after those preloading operations. But considering that it's an industrial facility, considering the critical importance of it, it was decided to construct rigid columns to bypass this fill layer. Once again, the available machinery governed the application and design, but this time it was definitely sufficient for our purpose, considering that we may not have a very critical problem at this stage. The client informed us that they could mobilize an equipment to construct continuous flight augers, CFA piles, CFA columns with diameters of 80 centimeters. So we can bypass the fill unit. So we accepted it, and considering the depth of foundation, well, below foundation level, the remaining thickness of the fill was in the order of 3.5 meters. Length of CFA columns were designed as 8 meters, approximately 10 times the rigid column's diameter. And by using the homogenization approach, assuming that reinforced ground will behave as a composite medium with better stiffness properties, the representative or equivalent rigidity of this reinforced soil was calculated, and by using the ground reinforcement tool of Settle 3, the settlement response was also evaluated as presented herein. We definitely performed some capacity calculations and reported them for the sake of documentation, but I will not cover them herein. But consequently, after those analyses, we realized that the expected settlements will be in the order of 2.4 centimeters and in all elastic manner. And the angular distortion, it will be in the order of 1/800, again smaller than the given limit. So they are in acceptable limits, and we documented that nothing serious was expected under this unit. And they constructed it, and fortunately everything went on as we expected. But let's talk about the last item in our geotechnical concerns list, and it was related to the seismicity of the project area. Well, you can see our current seismic hazard map, which was prepared by disaster and emergency presidency of the state. We are living in a seismically active country. It was what I said at the beginning, but it was true. So for each project, we have to take into account this issue and follow the regulations of our building earthquake code. Right now, we didn't have anything for the industrial structures, but generally we are following the recommendations of this code, and whenever they are applicable, we also use some international codes as well, considering the general hazard, considering the risk associated to it. I guess these figures give you an insight about the seismicity of the project area. Our project area is at the northern part of the country, and the expected PGA value, it is in the order of 0.22 G. I'm sure some of you have followed it, but 17 days ago, we experienced two major events in the same day. Two major earthquakes. One of them, it is 7.7 or 7.8. They are reporting two values. I'm sure in a short time we will get the final value. And the other one is either 7.7 or 7.6. They are major events, and they happen in the southeastern part of our country at this region. And the expected value, expected PGA value, I know that there exist some other components of seismic design as well, but I just want to provide you an insight about the degree of the problem. Well, it was 0.57 Gs. Nothing about the site soil conditions were considered while reporting these values. They belong to ZB type, B-type soils, especially some weathered rocks. And as Dr. Yunatcı, Anıl mentioned at the beginning, we are living in Ankara, at the central region of the country, so we are in a relatively safer environment. But even for this yellow region, the expected PGA value, it is varying in the range of 0.1 G to 0.15 G. So they are critical values, and for this reason, we have to think about it as well in almost all of our projects. So structural design was performed by considering the codes. There exist some parts about it in our geotechnical design as well, but for a geotechnical engineer, the critical issue is generally the liquefaction, considering that our site is quite close to sources of water, to Black Sea, and there exists a river in quite close proximity. So we have to think about it. And as I mentioned earlier, at certain regions of the project area, our alluvium, well, it involves some potentially liquefiable layers as well. I mean cohesionless soils, so we don't have a doubt they are liquefiable by their natures. But in this case, we have silt and clay mixtures, but they can be potentially liquefiable as well. So we have to think about it as well. For screening purposes, we used both the recommendations of our code and at the same time some literature as well. Here you can see one of them, which was proposed by Professor Seed and his colleagues. It is using plasticity index and liquid limit, the Atterberg limits of the soil, along with the natural moisture content of the material. There exist two zones. If you are in this red box, well, probably you will experience a liquefaction problem. You have to, at least you have to perform triggering analysis. But if you are in the blue box, further cyclic testing is recommended. But first you have to check the water content to liquid limit ratio, and they are varying in the range of 0.7 to 0.8. They are lower than the given criterion, so we say that, okay, we're not expecting liquefaction based on the provisions of this study and our own code. But one thing, some information, as I mentioned, we experienced two significant earthquakes And based on the early findings of the recon studies, they realized that silt and clay mixtures are potentially more susceptible to liquefaction compared to what we thought before. But when we performed this study, it was more than 1.5 years ago, and our material, well, it was really plastic. So at least for this part, it was not a problem. But whenever we had this problem, we definitely performed some triggering analysis, considering the results of seismic hazard assessment studies to check to see the relevant seismic scenario. If liquefaction is a problem and if we can't treat it, if we can't improve the soil, then we consider the strength loss for our stability or capacity calculations. We did it for some structures. For pipelines, we determine the lateral displacements or settlements depending on the geometry of the site by performing some more sophisticated analysis and again by using the semi-empirical approaches as well. But they are the stories of a different event. When we started preparing this presentation, we didn't have those earthquakes. And the last 2 weeks, well, although we weren't affected by these events, we are living in a different environment right now. All of us, we are trying to focus on those fields as well. So I didn't prefer changing the material, but I just want to mention these issues before concluding my words. And even for some soft clay deposits, very soft clay deposits, we evaluated the cyclic mobility potential of the material by performing some site response analysis as well. So they are just kind of spoilers. If we are invited again, we can talk about it. But right now, I would like to stop and I would like to leave the word to Dr. Yunatcı for his contributions to this project, its monitoring phase, but more importantly, to the presentation of the second case. Thank you.
Tolga Hocam, thank you. As a gentle reminder, while you're taking a rest, there are a couple of questions in the chat box. You may want to have a look at them. Meanwhile, I am back once again and checking my clock. I think I have to wrap up the second session within a rush. I wish me luck.
Okay. Sorry, Anıl, I used lots of time. I just realized that. I'm really sorry for it.
Help me if I need some help, Dr. Tolga. Case study 2, yes. It's in fact a field instrumentation-based performance verification of an improved soil site. The situation is somewhat similar in terms of the precautions and mitigation measures taken at the site. Now we're inviting you to a different part of Turkey. This is also an industrial plant. It was designed to have a 2,500 tons per day production capacity of paper. So the image, the satellite image you're seeing over here is the recent version. The project has been completed during the time that we were operating there in terms of providing the geotechnical engineering services, some design services, as well as consultancy and monitoring and quality control works. It was just open field. In a moment or two, you will be able to see the former version of the lot. So the production mill was going to hold sensitive equipment of up to 150 to 300 kilopascal static loads, and the allowable settlements were limited in terms of the total settlements allowed in the facility. So some of the rafts foundations were really huge, and the widths ranged between 18 to 165 meters. So An independent site-specific seismic hazard study was conducted in the region, as the facility was to be located within 2 kilometers. This is no joke. It was just actually 2 kilometers proximity to an seismically active fault. And in the recent maps in correspondence with our site-specific study shows for a 475-year return period of peak ground motion at a reference B-type site, we are around 0.42 Gs in terms of design considerations. In order to increase the bearing capacity of soft soil, which I'm going to talk in a minute, in order to mitigate the effects of possible liquefaction triggering and bring the site to a safer condition, an optimized pattern of drilled concrete rigid columns, an impact-typed rammed aggregate piers, and GCC columns were designed for ground improvement. This is how it looked before the construction began. The soil investigations, part of the soil investigations were carried by Geodestek. The borehole-based studies were not done by us. However, we received the data in a consistent manner. And I should have to state that the reference drilling rig used for that purpose approximately just possessed a 45% hammer efficiency. That's why we are reporting in terms of N45. So total number of 21 boreholes were drilled. The Menard stiffness modulus, pressure meter modulus of the soil samples at the top 10 meters varied from 5 to 7 megapascal, rather soft units, and artificial fill was followed by deep alluvial deposits. There was mainly presence of low plasticity clays and silts, with plasticity indices varying around 17 to 23, and with some amount of sands near the ground surface having varying thickness. In this simple idealized profile, I have just preferred to show sand units lying between 3 to 5 meters. However, this is not the case. At some places, some locations, it was evident that the sand layer was penetrating as high as 8 to 9 meters. Nevertheless, before any construction or design works were finalized, we were able to just probe 8 CPT tests all around the the facility, in order to calibrate our results with respect to the borehole-based investigations. And the 2 red squares you're seeing over here belong to indicate the sites that we performed more focused quality assessments and performance verification of the final design and production that was realized. A gentle reminder of the natural water contents and the consistency limits, as well as the fines content of the material that was evident in the field. This is to be followed with a general understanding and overall look of the CPT test results that we obtained before any remediation and soil improvement at the site. So pretty much we experienced a coherence with the borehole-based studies, as well as an general agreement between the CPT soundings we performed over the site. So not to just make a mistake, I want to remind here that the pore pressure labeling here at the CPT belongs to not the static pore pressure, but the U2 shoulder pore pressures directly measured during the time of CPT probing. Another evidence of the distribution of the soil classifications from the CPT soundings So we are just living in the world of some clays and stilts and with some sands. So very good agreements between the results. At the next step of the project, after the design was finalized, I don't want to take too much of your time because the design phase was another story. It was concluded to produce impact type rammed aggregate piers of having approximately 50 centimeters diameter and 18 meters length. They were augmented by the use of geoconcrete columns of smaller dimensions and same length. However, in order to just ensure that the loads were transferred to more rigid layers, a drilled concrete rigid columns of partly 80 centimeters, elsewhere 1 meter diameter and 40 meter lengths were used over the site. So the spacing was optimized and the sequence of the production was optimized, and a gentle quality assurance plan, control plan was realized to assess over each stage the efficiency of the ground improvement measures were taken. So in order to do that, one of our methods was just to conduct seismic CPTU tests supplied with surface geophysical testing at every stage of ground improvement phase. So we use these site data for shear wave velocity profiling to see if we have achieved something significant, notable, and remarkable in terms of an improvement at the site by measurement of surface geophysical methods and borehole-based geophysical methods, thanks to the SCPTU equipment we have. This is just a glimpse of our equipment and what we were doing at the time of quality control. A general overview from the site. That's the fault I'm talking about, located at 2 kilometers away from the site. And while we were just conducting the tests at the remainder of the site, the production operations could not be halted. We only had a chance to just temporarily pause them for a few minutes while we were taking surface geophysical measurements. They were operating literally night and day. Another photo of from the field works. So the sequence was as follows. First, the board pile was extended to a depth of 40 meters, constructed at the center of a ground improvement test area. The pattern was more or less homogeneous over the major structures considered. However, the pattern for improvement was optimized in terms of spacing with respect to the structural loads imposed by the other components of the facility. So over the lot itself, the pattern was not the same all over the area. So we already had the pre-improvement CPTU test completed at that location. Then as a second step, the GCC elements were installed, and after about a month after the construction of the GCC elements, the first phase of the post-improvement CPTU tests were executed. I will just try to explain now at which exact locations those soundings were performed in order to, for you to give an idea if we really got something solid to talk on in terms of engineering significance. And as the last step, the rammed aggregate piers elements were installed, and 15 days after the construction of those elements, second phase of the post-improvement CPTU tests were executed. These just nice sketches and drawings are taken from another reference which was published elsewhere. However, at the numbers you see in red marked as 1 2 and 3 shows the sequences of the pattern at the test area you are just observing. So literally we had the CPT B2 before the rammed aggregate pier element was already installed there. Then after the installation of the GCCs, we had a chance to just shift the location of the CPT as CPT P2, and within 25 centimeters proximity of the initial location, we performed another test at that location, which is labeled in red, as you see in the CPT sounding graphs. And after the rammed aggregate pier was installed, due to the nature of the production of that element, we hesitated to go closer to the periphery of the wrap element. So we had to keep away a little bit, at least at 40-45 centimeters away, so that we could actually get a CPT sounding there, not disturbed by the rammed aggregate pier elements and the expanded region composing of introduced aggregates in that region. So just to shift you further to the graph on the right, we have just observed almost a 27% increase in the tip resistances along the sand layer after the GCC columns were installed at CPT P2 location. However, we observed a marginal further increase at that location after the rammed aggregate piers were installed. However, please note that we had to switch the location of the CPT sounding a little bit. I would predict that we would have some further increase in improvement due to after the application of the rammed aggregate piers. Looking back to the U2 type pore pressure distribution. Here you can see a specific dilative sand response after the first phase of the improvement. However, as the third stage after the application of the rammed aggregate pier, a little bit of marginal increase in the pore pressures along the sand layer was observed. I should remind you that the last phase of the sounding was conducted approximately 15 days after the rammed aggregate piers were installed. In literature, we have just come across some evidence that the excess pore water pressures induced due to production of the RAPs may last as long as a month or so. So in case we had a chance to make another CPT sounding approximately 1 month later, maybe we could have observed somewhat different results. So that was just to conclude the performance verification of what all those improvement columns had produced. Another way of validating performance through field testing was done to design by designing a very simple surface loading pattern, which was kept wide enough to cover at least one repetition of the pattern we had there. The selection was made, the site selection was made a little further away from the first test site. The surface loading was applied on a 3 by 3 meter location, and it represented the actual design loads at 100% scale. Thus, we had to place 170 tons of dead loading within a day to just ensure that the settlement phase under the real loadings had been initiated over an improved soil site and see the performance. So if anything went wrong, we would have a priori information about the performance of the raft structures, which were very sensitive to settlement, and think of another way to just overcome any potential problems in terms of total and differential settlements. We were able to see that the 90% of the total settlement was completed within 36 hours of completion of the design basis load. We had a chance to track this by just monitoring the surface settlements real time. All equipment was kept at the site, and we had a chance to monitor it real time with a 10-minute sampling rate, just sitting in the comfort of our offices, getting data and just discussing about it over a cup of coffee. While just interpreting the results, we of course downsampled those data to 1 hour intervals, as this was seemed pretty sufficient. So thanks to the system we built, we had an uninterrupted operation during 1 month period. And thanks to the responsible people at the site, that they were kind enough to offer and provide us the necessary physical and logistics to keep the system up and running without any interruption. I should state that the surface settlement pattern measured along the 4 edges of this block shows somewhat of a slight differential settlement overturning along a prescribed axis. However, the overall settlement magnitudes and the average settlements gave us pretty much impression about the performance of what is to be expected. So the next thing was to basically calibrate our settlement prediction model based on what we actually measured at the field from a test site. Please recall that you have numerous variables to play around with to calibrate a numerical model, but we didn't bother to dive into those discussions and kept it very simple because all of the evidence was already existing in the field. So it was a great chance for us to at least get an impression of the elastically settling part and improved part of the region after the ground improvement measures were taken. So we moved on to prescribed and suggest other system variables to the structural designer based on what they had and tell them if they needed further precautions. This is simply some not analysis based or empirically based suggestions of moduli of subgrade reaction, but an actual representation of the modulus of subgrade reaction based on what is evident in the field at a level of deformations under static loads and dead loads. Another question which arose was to have an estimate on the modulus of subgrade reaction at lower shear strains under the effect of operating machinery at the paper mill. So we took this opportunity just to dive deeper into the modulus, shear strain, degradation properties of such soils, which are evident in the field as published before and just validated numerous times in the literature, and extrapolated and used this behavior to come up with the estimates of the KV value subgrade modulus under lower shear strains based on what we got from a dead load behavior. So I think this was simple enough, a very basic application of how you can use basic monitoring techniques to back calibrate your models, to see your field performance, and move on and just proceed with the rest of the project with a solid evidence in your hands, so that in case something unexpected happens during the next stages of the construction or operational phase, you will have a pretty good documentation of how the performance of the ground improvement had been documented and verified. So this concludes my words for the presentation, and we thank you for your patience and hand the stage to maybe Hamza, who is the moderator, to forward us some questions if the audience has. Thank you. Thank you for listening.
Hamza, you are muted, I guess.
Yeah, sorry.
I guess mute again.
Yeah, sorry. So we have maintained almost 80 people till the end of the presentations, which is good. And indeed, there are some questions from the beginning. We can scroll them. Okay, so Muhammad Hamza is asking, do you provide and install horizontal inclinometers? I think this is a general question, maybe not related to.
Okay,
directly.
Tolga, let me answer. The simple answer is yes, we
please.
do. Please say hi to us and we'll talk about the details.
Okay. And then Astrid asked, did you define the scope of the investigation? I think somewhere in the presentation
no,
you
actually,
said no. Yeah.
Yes, no, we didn't. And as far as I see, the remaining questions come to me, and while talking excitedly, seems that I missed some points. So thanks for this, these questions, and let's answer them one by one.
And again, Astrid asked, did you provide the spring stiffness for the structural analysis? The one
yes.
you have shown?
We did it, and remember, while talking about the use of rigid columns, we mentioned that they may not be necessary, but they definitely help us to optimize the foundation design, because by this way we had a chance to increase the spring constants, and we definitely reported them for the structural designer, and they were used.
And then Dino also is asking, were the settlements due to the filling considered, because the fill load is huge, approximately 140 kilopascals, so, and they were monitored. I think those was asked early.
Yes, and yes, actually the first two phases, I mean the ones that were completed in year 2016 and year 2021, they were not monitored, but the settlement response under the additional preloading, the 5-meter hard embankment, it was monitored by using settlement plates.
Awesome. For that, we could probably use the remote sensing monitoring, but we will have a separate talk about that later on. Okay. And then again, Dino also is asking, was the secondary consolidation considered, if there are any secondary consolidation?
Well, actually the material, although it was quite close to the coast region, it was not organic in nature, but relatively higher plasticity index values were reported. They had some creep tests. I didn't show them, but it was stated that it was not expected. So for this analysis, we didn't think about them, but it was a critical point. And considering that they kept the additional preloading embankment for a prolonged time, and I guess it was useful against this problem as well, but later they remove it. It was something that I missed while talking about the story, and I realized that there exist some questions associated to it as well.
Okay. Also, Astrid referred back to the settlement response under structural stresses formula. She said it might be a repetition of the E.
Yes, there exists a typo. Thank you, Astrid. You catch
picked
it.
it up.
Yes,
Yeah.
yes. And it's good to see Astrid. We met 3 years ago at Oman for a educational series about rock science. Great to be with you, ladies and gentlemen. It's really a huge pleasure for us, and thank you for those questions. Okay,
then Wael also is asking which method have been used for the field settlement observation analysis? Is it hyperbolic or?
Well, we are generally, in Turkish practice, people generally preferred using Asaoka's method, but we also checked the hyperbolic model as well. They were not that different. Actually, Chang and his colleagues proposed a solution in year 2009. We used it along with Asaoka, so we checked both of them.
And again, Mohammed Hamza is asking about the CFA piles that acted as rigid inclusion almost in a similar manner to strengthen the random fill. And he's asking what was the estimate of the total consultation settlement?
Well, it is the point that I realized that I didn't mention. They removed the additional fill. So when they started constructing those CFA piles, it was just 3.5 meter fill and then the alluvium. So they bypassed the 3.5 meter fill and 5.5 meters in the alluvium, and the expected settlements. And by the way, since they removed this 5 meter thick embankment, it is the reason why I mentioned we were not expecting any additional consolidation settlements. Right now, it should be totally over-consolidated material. So the settlements, they are in the order of 2.4 centimeters, but I think it is elastic because we already loaded the soil by 140. Dino made this calculation and mentioned it in his question. So it was the case.
And someone is also asking about, I think, Abdurrahman, how did you model the sand drain columns?
For the settle tree, they have the drain column tool. It is allowing us to define some values. And since we have field verification data, and as I mentioned, it was not the first project that we use. Actually, we got a chance to verify our findings while working on some other parts of the study. So we have an idea about the permeabilities of those materials or the smear zone effects. So we got a chance to define them by using the input screens of settle tree.
I think we covered most of the questions. I have just a couple of questions. Have you considered finite elements in addition to the settle 3D? And this is one. And the second, was it viable to use the vacuum with the drain? Like if you used PVD with vacuums?
First, we didn't have a chance to use these weak drains. We got some primitive sand drain columns. I know these vacuum applications, but they are not very common in Turkish practice. Although it was an international project, they didn't think about use of prefabricated weak drains. So unfortunately, it was not a case for this one, but it is definitely possible. And regarding the second question about using the finite element solutions, well, first of all, settle and its consolidation settlement module, well, it includes a hidden finite element tool in it. But we didn't perform any other calculation. but as I mentioned, we were responsible for some of the structure, and there exist two designers. The other team used a different software. I'm not going to mention its name, but you can guess it. It is definitely popular. It is definitely strong. And at the end of the day, the results, the findings, well, they are quite comparable. So it was possible, but since we have this verification, we didn't need to do it as an additional thing.
Awesome. Awesome. Thank you, Dr. Tolga and Dr. Anil, and everyone. Please, if you have any question, you feel free to unmute or to discuss anything. Otherwise, we should conclude this fruitful session.
Excuse me.
Yes.
Can you bring up
I think that's it. It seems no one has any further question. Thank you again, everyone, for attending, and thank you, Dr. Tolga and Dr. Anil, for this presentation. The recording will be available for those who is asking for the presentation files. There is no point of sharing the presentation files. I think if we are sharing the recording, and the certificates hopefully will be available soon. Work on that hopefully with GEG and Astrid, of course. So, thank you, and see you in GeoTalk 3 soon.
Bye-bye.
See you soon. Bye.
Bye.